pleasure to be back in India among so many old friends, many of them citizens. And so it's really great. I better put this as it should go, which is to play it. Okay, so in this it's a tall task to try and cover all of cosmic theory in 45, or an hour and 45 minutes. Isn't that how much time I have? This is, as are many of my slides, meant for their to be unreadable. And for those who know me, you will nod at that. This is one of those classic diagrams where you go from now and you go back and galaxies created here. This is another way of looking at it, a more theoretical way of looking at it. And I'm going to touch on topics in each of the areas as we look back from where we are now, going through the Milky Way. I won't say much about the Milky Way. But as we move back, there is a period of when the dark energy comes to dominate, whatever the dark energy is. The nonlinear cosmic web starts to grow with the waves of density crashing together to produce the cosmic structures. As we work back, there is a period of reionization, presumably from first stars, possibly something else, redshift of order 10. We work back further and we go to the decoupling last scattering surface of the microwave background, which propagates to us, carrying information about geometry as well as much in terms of the specific physics of the photons. And as the radiation propagates to us, it passes through all of the intervening nonlinear stuff to generate all sorts of new imprints apart from the primary anisotropies here on the microwave background, which we can use to learn about all sorts of aspects of the universe and have been used to good effect already. For example, weak lensing, we'll hear more about this later, and I'll mention it very briefly in passing here. The thermal Sinyaev-Zeldovich and kinetic Sinyaev-Zeldovich effect, in which the photons are being upscattered through just simple Compton scattering as they pass through hot gas, and because the hot gas is inhomogeneously on the sky, it means that you can get a delta temperature signal of it. There are all of the really interesting extragalactic objects, which at some level are a curse and another level a joy. A joy if you're specifically interested in them, a curse if you only want to know what's primary, because it's in the primary that we get the information of the ultra-early universe, the inflationary epoch. And so that's when we march back very much in time to 13.7 minus 10 to the minus 50 or so gigayears, the inflationary epoch. And I'm also going to highlight in the talk of this talk, in the course of this talk, two epochs of entropy generation. There could be more as we pass from this period through to photon decoupling. We have constraints on that it can't have happened too late, because we would have seen it in distortions of the microwave background. But there are quite likely to be, if the theory of inflation is at all correct, there will be one major entropy production period, which is fundamental to human existence. It's come to be called preheating. And then there's another entropy production period associated mostly with the crashing together of the waves. Here is the iconic Planck released a one-year all-sky map that is artfully constructed so you can't Fourier transform a figure of it. And our good friend Francois Boucher will be describing it in much more detail. Just to note that it was veiled, and the number of veils, count them, is about 7, and they have to be removed veil by veil in order to denude the image in order to get at the fundamental physics that lies behind. By the way, this is a talk that involves me, and I would like to say a cast of thousands. Namely, I cannot name names because there are far too many names to name associated with the whole development of the theory of the cosmos, obviously. Okay, But topics I will hit upon. One, which I'll come to a little bit later, is inflation histories. That is to say, the history of acceleration in the ultra-early universe. And there are the various probes are listed below it that tell us about this. What we look for in these inflationary histories, apart from, you know, the dramatic bow down to the lambda CDM model, is subdominant phenomena. BSI means broken scale invariance, which might be a gentle breaking, that's NS not equal to 1, or radical, it might have bumps in the primordial spectrum of perturbations. And there could be other modes present from the ultra-early epochs. As well, fundamental, and now there's an army of people that are working on this. It's trying to work out signatures of non-Gaussianity, very, very weak in form because we would have seen it. Otherwise, it would appear in the primordial fluctuations. It appears ad nauseum in the non-primordial fluctuations. That is the nature of non-primordial fluctuations. High non-Gaussianity, let's just think of the Milky Way itself. I'm going to talk a little bit about it, but David Wands is going to be doing an entire focus on that. Then another very, very exciting thing is gravity waves, just like we heard about. Gravity waves is fundamental from the point of view of extreme gravity, but it's also important from the point of view of the early universe. And CMB polarization is one way to look for it. And so there's a huge number of experiments that we're involved in all of these that could have something to say about the gravity waves. And the basic figure of merit that people use is an overall amplitude expressing the ratio of the power in tensor fluctuations relative to scalar fluctuations. It's called R. But actually, it's a direct measure of the acceleration of the universe at that early time. There is something that I won't actually spend much time about except in this little box here, which is recombination histories. Now, if we are going to do precision cosmology, we have to have gotten the theory of the hydrogen and helium recombinations very, very well indeed, because otherwise we will screw things up. And there was a major change. It may seem like a minor change, but it was a major change that occurred recently from Jens Kluba at CETA and Chris Hirata and collaborators at Caltech. I called it Hiratarek because I couldn't remember the name of it, but it's got some fancy name. Jens calls it Cosmorec, and then there was some other, RecFast was the old version. And if you got that wrong, it shifted the cosmological parameters. Okay, so now, given that you have now refined your theory, including hundreds of hydrogen lines as part of your calculation of recombination, what if you didn't get that quite right? What if there's new physics? What if there's a little bit of energy injection to change the nature of the recombination? So what we've done recently at CETA is to do a relatively semi-blind eigenanalysis of the recombination histories, and we hope that our good friends, including me and Planck, will actually apply this kind of technique to place constraints, which they do, on how recombination actually occurs, what errors are allowed for the history of recombination. It might not surprise you that the focus of that information is all in town, which is an old game. It's called Modify Einstein Equations, and we put in his mouth 9, but then we put in his mouth yeah, because he says, okay, just go to my frame, the Einstein frame. Gravity looks absolutely normal. It's just that what you've done is made a bunch of fifth force interactions. And that's another way to look at this whole game, and one that's actually quite compelling, because then you can use more of your intuition, not that it isn't completely reciprocal. And I was going to pay obeisance in this discussion, but I don't have time because my conductor is saying there is no time, to the great role that Giant Narlikar played in, with Fred Hoyle in really emphasizing the role of conformality in cosmology. So if you go to Mr. Einstein's frame, you get an Einstein equation which has the logarithmic derivative, or the derivative of the Lagrangian, if I'm just doing of f of r gravity, with Einstein's Lagrangian times T mu nu of the matter, and then a new field is introduced. Yeah. So there are interactions. Okay, we have a new way of looking at it. Okay, so I'll end on where we began. Unfortunately, I didn't get to tell you all of the story because he didn't give me my an hour and 45 minutes. He cut me off at 45. Okay.
So thanks for a very nice talk and a review. So one or two questions?
Is it correct to assume that the warm dark matter model is now totally out of the picture?
No, it's actually come back. It has a tendency to come back again. So Jim pointed out some of the possible small-scale problems with the standard cold dark matter problem, and more have arisen over time. And so even stalwart cold dark matter people like Carlos Frank have been dusting off the old warm dark matter models and reapplying them. But of course that gives you one other degree of freedom, which is that you've got the temperature of that warm dark matter to play with, which is related to the mass of the warm dark matter. So yeah, they're totally back in, but what is clear is that you can't make that temperature too hot. No going back to hot dark matter. So it's just a question of how warm you allow it to be so that you don't upset the huge agreement that we get over a vast range of scales. And then the other point that I always raise, which everybody should always bear in mind, is that in spite of the fact that we're talking about kiloparsec to megaparsec distances, from the point of view of cosmology, this is short distance structure. And it can be, that was created mostly early on, and gastrophysical processes can have a huge impact on upsetting the situation.
So if you could just say a few sentences about what really is known at all or not known about the reheating phenomena in which the inflaton energy is converted into the standard matter,
Right.
standard model.
So I can just tell you what's being, let me briefly give, very briefly, the history. So when we first started this game, there was the standard thing where you just put in a slow drag, and people have been using it. It's called warm inflation. It's kind of silly, though. What you have to do is to couple the equations to some other degrees of freedom, and it has to be a coupled field theory process. So that was a game which Kaufman and company basically initiated, and we've been doing that more and more. So what has been looked at? There have been some simple couplings, like the simplest is a phi squared, chi squared kind of coupling. There have been other ones that have been used. That roulette inflation didn't require any. It turned out that the potential was such that it sort of did it for you. People have tried the most important coupling is with a fermion. Most important coupling with is an f squared kind of term, f mu nu, f mu nu. The problem is nobody really, as far as I know, has any idea of how it's going to couple to the standard model or anything like it. So what happens in these simulations, which create this sort of cascade of modes, a beautiful spectrum as a function of momentum, it's very far from a thermal state, and it is very slowly evolving. Eventually it will get to the thermal state. But what we need is something in there which I think accelerates the movement to the thermal state, because there's just a long way to go from where we get to with the simulations to where we know it got to, which is a thermal bath of quarks and gluons and other such things. So that's a big problem, but it's sort of obvious since we don't know what the inflaton is, we don't know what couples in the inflaton, and we don't know what the ultimate interactions are.
Okay, let's time the speaker.